Hello, and today we'll be talking about Section 3, Model of the Atoms and Isotopes. So first, a brief overview of atoms. All matter is made up of atoms, and the idea of the atom goes back to the ancient Greeks. So essentially, atom is in Greek for indivisible, and was made up by the Greek philosophers Democritus and Leucippus. And they came up with the basic principles for the atom. These were that everything is made of atoms, atoms are invisible and indivisible spheres of matter, and that there are an infinite number of atoms and number of types of atoms. However, as you can see, atomic theory clearly changed over time, and these principles may not be true now. Dalton's model was coined in 1803, and his ideas were based off the ideas of the ancient Greeks. Essentially, he said that atoms were hard, indivisible spheres, and atoms of a certain element were identical. Dalton proposed that atoms of different elements could be differentiated by their weights, and the elements could combine to form compounds. He also said that atoms cannot be created or destroyed when they combine to form compounds in a reaction. As you can see here, we have an image of Dalton's model of the atom, and we have an image of Dalton's proposed combination of atoms to form a compound, such as a water molecule. Now next was J.J. Thomson's model, which was coined in 1897. He discovered electrons while investigating cathode rays. Essentially, what a cathode ray is when a ray is emitted when a high voltage source is applied to two electrodes. And this ray was attracted to positively charged metals and repelled by negatively charged metal. And ray particles within each ray was found to be 2,000 times lighter than hydrogen. So J.J. Thomson deduced that the particles present were present in many types of atoms by changing the types of metal, and he was able to find that the cathode ray particles still emitted were identical. He called these particles a corpuscle, and in 1904 he proposed the plum pudding model. The atom was a sphere of positive charge with electrons spread out within. Rutherford's model was found in 1908 and was actually intended to confirm Thomson's model. So essentially what he did, he fired alpha particles, which is helium-42, at a thin sheet of gold foil, which is only a few atoms thick. And these particles were small enough to actually pass through the gold foil and should have been able to do so easily with little to no deflection if the Thomson model is correct. And let's go back to the Thomson model really quickly. It is a spherical cloud of positive charge with a bunch of electrons floating within. As you can see, there should be no interference with the alpha particles. So the alpha particles should go straight through. However, most particles were able to pass through, which would confirm Thomson's model, but in fact, some of them were actually deflected at large angles, which does provide some controversial evidence to Thomson's model, if you could say that. This led to the conclusion that the positive charge was concentrated in the center of the atom rather than spread out. So, most of the atom was empty space, and as you can see, that is what the model he came up with. It is a model where most of the electrons orbit the nucleus, which is the center of the atom. However, this model had a little shortcoming where it failed to explain why electrons orbited rather than spiraling into the nucleus. Bohr's model was created in 1913, and he wanted to solve the issues with the Rutherford model, such as why the electrons orbited instead of spiraling into the nucleus. So he used quantum theory to explain the arrangement of electrons, and proposed that electrons were in quantized energy levels called shells, and that electrons could move between these shells or energy levels, or rather what their stationary state was, by absorbing or releasing energy. Bohr's model worked for hydrogen, but not for larger atoms, which was a problem, as it violated Heisenberg's uncertainty principle, which was actually found after Bohr's model was created, so technically it didn't violate it at the time. However, Bohr's model is used as a simple way to explain chemical bonding and reactivity, and is usually the one most commonly taught. And as you can see, there's a nucleus followed by a first shell made up of 2 electrons, second shell made up of 8 electrons, and third shell made up of 18 electrons. Schrodinger's model was created in 1926 and proposed that electrons behave as waves similar to light-wave particle duality. So this model is actually the most accurate model and proposes that the nucleus is surrounded by clouds of electron density. Clouds of electron density are clouds where electrons are actually likely to be found. So you don't know exactly where the electrons are, but you just give a general area where they are probably are. So it doesn't violate the uncertainty principle. And the clouds of the electrons are called orbitals. Other important experiments in determining a model of the atom was Robert Millikan in 1908 with the oil drop experiment, who suspended charged oil drops between two electrodes and used density and mass from observed radii of the oil drops to calculate the charge of the oil drops. So essentially the calculated charge was 1.5924 times 10 to the negative 19 coulombs, while the actual charge is 1.602 times 176487 times 10 to the negative 19 coulombs. As you can see, he's actually very, very close to the actual value, meaning that his experiment was pretty much accurate and set an example for the charge of the electron. James Chadwick in 1932 found out that there were neutrons in the atom. So essentially what he did, he put beryllium in a vacuum chamber with polonium, and beryllium emitted neutral rays when struck with the polonium's alpha rays. And this is very similar to Rutherford's Goldfoil experiment, except for the fact that the beryllium is emitting instead of the alpha rays being deflected. And now we move on to the final topic, which is isotopes, atoms of the same element with different atomic masses. Atomic numbers stay the same. Proton numbers never change within an element. If you change the proton numbers, then you get a different element. So an isotope does not vary the proton numbers, rather it varies the neutron numbers. For example, carbon-12 has 2 less neutrons than carbon-14 and 1 less neutron than carbon-13. However, these isotopes sometimes are radioactive due to the fact that they are unstable with the extra neutrons. Carbon-14 loses its extra neutrons over a period of 5,730 years to become carbon-12. And other examples of radioactive elements also include like neutron loss. This is called beta decay, and can sometimes involve neutron gain, which is called positron decay. No, actually, I'm not sure about that. Don't quote me on that. And the variation in electron number does not affect atomic mass either, as variation in electron number causes ions, or it could be associated with different elements. And since electrons are so small compared to the neutrons and the protons, electrons being 2,000 times lighter than helium, they won't affect the atomic mass at all.